Okay, so now we're going to do another example. And so this example involves the Alaskan pipeline. So crude oil is pumped through the Alaskan pipeline. And so for the crude, the specific weight, which is equal to rho times G, is equal to 53.7 pound-force per cubic foot. And the viscosity equals 8 times 10 to the minus 5 pound-force seconds per feet squared. And it's a steel pipe. And it's a steel pipe. Okay, and the length of the pipe is 799 miles, so it's very long. And the diameter is 4 feet. So it's a very long, huge pipeline. And the volumetric flow rate is equal to 2.4 million barrels per day, and if you convert that to a more normal unit, that is equal to 117 cubic feet per second, which is a whole lot of oil flowing through that pipe in 1 second. And so we are, what the problem is asking is find the amount of pumping work that is required to move the oil through that pipeline. Okay, and so the solution, again, we'll assume steady, constant properties, etc., etc. Okay, and so the solution is, just for completing it, you could imagine we have some sort of a reservoir in Alaska where we're pumping the oil via a pump. Actually, lots of pumps, not just one, and we're pumping it to another reservoir somewhere else. And this length here, L, is 799 miles, and the diameter, D, is 4 feet. Okay, and so essentially here we're going to draw our control volumes. We're going to draw our control volumes. You could, and Q is going through the pipe. So you could pick states 1 and state 2 to be out, in, or you could pick them to be here. It really doesn't matter. Okay, and so I will just choose them. I will just choose state 1 and state 2, the inlet state to be here and the outlet state to be here. You could choose the inlet state to be here or here. You will get the same result in the end. And the outlet state to be here or here, you'll get the same result in the end for this particular problem. Okay, and the reason being is that, so we do our little control volume, and this is implicit for these sort of pipe flow problems. And we use our energy equation like we always did before, and we'll assume a fully developed flow. Okay, and that was an assumption for the previous example that I forgot to mention. And so with all these assumptions, we can use the energy equation that I derived in the previous lectures. So that's P over rho G, and rho G is just gamma, plus alpha U averaged squared over 2G plus Z at the outlet, minus P over rho G plus alpha U averaged squared over 2G plus Z at the inlet, equals W dot pump divided by M dot G minus any turbine work divided by M dot G minus the total head loss. Okay? And then note, you could argue that if you pick the inlet and the outlet state here, P is going to be the same, or P is going to be different. But so basically the average velocity is going to be the same here and here. So that's gone. They're at the same elevation, so that's gone, and the pressure is gonna be the same because of the pump. Now, what you could do, and alternatively, if you chose state 1 and state 2 to be here and here respectively, then the pressures are the same, so those cancel out. The velocity squareds are both 0, and the elevations are at the same height. So again, it just simply doesn't matter what you pick. So basically, these are the same. So they cancel out, and just as long as you choose the inlet and the outlet consistently, that works. And there's no turbine work, so that's gone. So we find that, that the pumping work, or the power that needs to be put into the pipeline by a pump, is equal to the mass flow rate times G times the total head loss. Okay? And so that means all of the energy that is being input into the fluid by the pump is just going into in the pump that's needed to drive the flow from basically one reservoir to another reservoir. All of that power, every last ounce of horsepower, is going into viscous flow losses. All of it. And so we need to find HTL. So need to find HTL, and the head loss equals the head loss due to major losses plus the head loss due to minor losses. Okay, and we are going to neglect the minor losses. And that's just due in part that the L over D for this is huge. So it is unlikely that the loss coefficient for the minor losses, KL, is going to be anywhere close to FL over D for the major losses, just due to the length of the pipeline. Okay, and so for this problem, we will neglect the minor losses, because for this type of pipeline, the minor losses are truly minor. Now, for mechanical engineering, we normally don't design big, massive pipelines, but in a hydraulic system for a piece of agricultural equipment or something like that, then as I showed in the previous example, the minor losses play a huge role, and sometimes they can even be greater than the major losses. Okay, so the major head losses equals sum of the Darcy friction factor F times L over D times U averaged squared over 2G. Okay, and so there's only one section of pipe, so this equals F L over D times the average velocity squared over, 2G. Okay, so we need to find F. Find F and U and the average velocity. Okay, well, U average equals Q over A. That equals 117 cubic feet per second over pi over 4 times the diameter, which is 4 feet, squared. And so the average velocity is 9.31 feet per second. Okay. Then we're going to need the density for the Reynolds number. So rho equals gamma over G. that equals 53.7 pound force per cubic foot divided by 32.2 feet per second squared. Okay, and I'm going to convert pounds force to slugs. So 1 pound force is a slug feet per second squared. And so the density is equal to 1.668 slugs per cubic foot. Okay, now we know the viscosity, which was given in the problem statement. We know U average, we know rho, and we know the diameter. So we can find the the pipe Reynolds number. So RED equals rho U averaged D over mu. Sticking it in the numbers, this is 1.668 slugs per cubic foot times 9.31 feet per second times 4 feet divided by the viscosity, which was 8 times 10 to the minus 5 pound force seconds per feet squared. And I'm going to convert the pounds force to slugs. Pound force slug is equal to a slug feet per second squared. And if you punch it, and if you punch the numbers into your calculator, you'll get that RED equals 776,450, which is much greater than 2,300. So it's turbulent. And in fact, it's very turbulent. Okay, and so what this means then is that we need to use the Colebrook equation. So need to use the Moody chart or Colebrook equation. And so to use the Colebrook, or to use either or, F is equal to a function of RED and the relative roughness. So we need the surface roughness for the steel pipe. And so from table 8.1, epsilon equals 0.00015 feet for steel pipe. So then the relative roughness, epsilon divided by D, equals 0.00015 feet divided by 4 feet, and that equals 0.40375. So we now know the Reynolds number and we know the relative roughness. So now we just use the Colebrook equation to find F. So use Colebrook to find F. And the Colebrook equation is 1 over square root of F equals minus 2 log base 10 of the relative roughness divided by 3.7 plus 2.51 over RED square root of F. Okay, and if you punch this into, if you put in epsilon over D and RED, you'll find, if you stick in the numbers again in homework, show your work please, you'll find that F is equal to 0.1284. Okay, and so that's what you'll find. Not 0.1284, 0.01284. Okay, and so we now know F. Then the pump work equals m dot times G times the total head loss. That equals, And m dot is just rho q, and that equals gamma q over g. Okay, so this equals gamma q g over g, those cancel out, times FL over D times U averaged squared over 2G. Okay, and so this is HTL a major for this case. Okay, and so we know that, and we can now stick in the numbers, then the pumping power, or the required pumping power, is gamma, so 53.7 pound force per cubic foot, times the volumetric flow rate, 117 cubic feet per second, times F, 0.01284, times the length, 799 miles, divided by D, 4 feet, and I'm going to convert miles to feet. And so 1 mile is 5,280 feet, times the average velocity squared, which was 9.31 feet per second, and I'm going to square the whole thing, divided by 2 times 32.2 feet per second squared. And then I'm going to multiply this by a conversion factor, that 1 horsepower is equal to 550 foot-pound force per second. Okay, and so we get that the pumping work is equal to 208,200 horsepower. Okay, and so this is a gigantic amount of horsepower that's required to move the crude through that pipeline. And all of that power goes into viscous losses, all of it. And so that's a substantial amount of power that is required, and that's all goes into viscous losses. That all is going into the wall shear stress at the walls of the pipe. And so that is a gigantic number.